Hello everyone, welcome back to the Game Engine Development Workshop series. So last time I went over sort of like a super fast, simple crash course in assembly language. And today we're going to actually start working on our scripting language, which is exciting. So I'll go over like a brief intro, just talking about why this is even a good step to take. Then we will look at the specification for our scripting language, and then we will actually start programming all of it. Okay, so let's talk about why we should create a scripting language. Like this is something that is going to be, running like on top of a layer of C++. It's all like none of it is natively compiled code. It's not running on your actual CPU. So it's going to be slow, right? So like, why even do it? Like C++ will just run faster, and this is absolutely true. In the benchmarking I've done for this specific scripting language, it's about 10 times slower than C++ code, which is certainly significant. But there are two reasons that this is like okay. And the first reason is actually because of all the other steps we've taken to making our engine super, super fast. Like all this stuff that, basically every time I said, well, for our simple case of a 2D game engine, like this is overkill, but it's the right way to do it. That's where all of that like comes into play, and this is the payoff, is that at this point we can afford to be somewhat inefficient. Like we still need to be smart about how we design stuff, but we have enough wiggle room that we should be able to like overcome the just necessary slow performance of any scripting language. That's because we have things like render batching and dynamic render batching. Those are the big two, but also hitboxes, especially for edge cases where you have tons and tons of stuff. Our engine handles that with ease. And so you saw last time I was running a debug mode even, and last time we were about 1500 FPS. We'll probably be about the same here, maybe 100 or so higher. But let's just see where we sit. Okay, yeah, so about the same. Um, but yeah, I mean, 1400, like no monitor is capable of displaying even close to that refresh rate. So you wouldn't have a production build of a game running at that speed anyways, because that's just a complete waste of processing power, and there's no reason. Um, so all those sort of like efficiency steps that we took earlier basically allow us to be a bit messy with this part, which is okay. But the second and like main reason that it's okay that our scripting language is going to be 10 times slower than C++ is because it's, well, there are sort of four smaller reasons within this main reason. The first is ease of use. Our scripting language is designed by us for like to do certain specific things, which means that doing those certain specific things will be very easy. It'll be very, very fast to develop functionality, whatever you want, like whatever we've planned for. It'll be fast and easy to develop that functionality with a language specifically designed to develop that functionality. Um, so that's like a pretty big reason. Um, from like a product standpoint, if you were like planning to release this game engine like commercially, which you definitely could not. I mean, you just can't compete with Unity or Unreal. But if you were, planning to release some game engine, anyone who downloads it is not gonna, have access to the source code, or even if they did, the knowledge of how to modify the source code or add source code to do what they want. And this also goes for, I think, the more common case of if you were working at a company and you were like on the sort of like core utilities team, like working on the engine behind the games. The game designers at that company who have to use this engine aren't going to have intricate knowledge of the engine itself. They won't, and they shouldn't be expected to. That's just like that's your job, right? And part of your job is making this thing fast and functional, obviously, but also easy to use. And so scripting language definitely helps out there as well. And I would argue is necessary. So, some type of not necessarily scripting language, more likely like just like a visual tool set, like a suite of tools. Kind of again how Unity and Unreal like the backends are these game engines, but really it's like a software package that you're buying. It's this whole like, I don't even know. It just has tons and tons of functionality built into it. The most important one though is development cycle, because even if we aren't, in this hypothetical scenario where you're developing this, designing this engine as something to be used by other people's, even if it's just for use by you, which is sort of the case that we're in here, scripting still makes your lives way easier. So like, this is something we don't have, but just imagine for a second that you get to the point in development where you have like a graphical map editor, um, and you can like you can load map files, you can edit them in some visually intuitive way, like you can pick a sprite to draw with, and then you draw on the background or whatever with that, and then you can save the map file back out. So that's great, but that only really handles the map stuff. So what if you want to sort of take this to the next level and you say, okay, so I want to add this certain type of enemy into my level here, and I haven't, this enemy type doesn't exist yet. Like I have to write the code for this enemy. So you would have to close the editor, write new source files for this, new enemy type, whatever it is, hook it all into the environment, make it so that you can actually create this new type of enemy through the GUI, the map editor. It's just like a whole long process. That's going to take, a long time, and there's so much trial and error there, and so much time is wasted just compiling your code, and then like reopening the editor, reopening the map file, getting it like the game into a state where you can then test whatever this functionality is. It doesn't work inevitably, and so you have to close everything down again, recompile your code. It's just a mess. But now step out of that nightmare for a second and imagine that you instead had the forethought to create some type of scripting language. You can like, if you want, you could even go as far as like integrating a script editor like into your map editor, just like a text file editor basically, or not. You don't even need that. You can just save the files. You can have them open in Notepad or something, or like VS Code or Atom outside of your map editor, and just save them in that, whatever text editor you're using. But then you don't even have to close the map editor every time you want to make changes to some type of like, I'll just call it dynamic functionality, is sort of the blanket term for anything scripted, really, like a camera moving around, the player moving around, new enemy types, new enemy AI. You don't even have to close the map editor, let alone, write new code, make sure all that code compiles, then go through that whole charade all in, like over and over and over again, to get it to work. You just like have this system that's there and ready to go. You can write your scripts, you can compile them on the fly, and every time you just like hit the play button on your map editor, you can test the new functionality right there. So that's the biggest one, is development cycle standpoint. This is like, I don't know how you would do without something like this. If you want, like any sort of sizable like real 2D game that has some degree of complex functionality. If you're just making like an arcade game or something, then obviously you don't need this. But for the general case of a larger game with more complex functionality that you're always going to be tweaking and changing and adding on new stuff, this is necessary. And the fourth reason is it's just really cool. Like, I love making neat tools. You heard me just go on and on about a map editor there, even though we're not making one. But I think like a custom programming language, that's kind of like the ultimate neat tool. Like what can you do that's better than that? A custom programming language? Come on. So yeah, those are like the main reasons that this is even good. And I'm sure that most of you like agree completely, and like you've thought about this all, because scripting was by far the most requested sort of like end game content that we would be doing. But I just wanted to go through all my thoughts on it to get everyone on the same page. Okay, so that's the intro. I wrote like a specification document here, just sort of outlining everything that our language does, and just it has all the different instruction types and all the different memory components that it needs. So we'll just sort of skim through this, I think, in the video, but I'll have a link to it in the description if you want to sort of pull this up, because it has like a list of all the different instructions and the arguments that they take, which will be really nice if you're just, well, if you like didn't design this, basically. So let's just start from the top and go the way down. I have this little legend here that might be useful to you if you want to pause and read that. So architecture, scripts are read in from a file. That's like the most basic thing, right? We have a text file, and we want to turn it into some set of commands that our game engine will execute. Each time a script is run, these commands are executed in order from the entry point, which is what I described last time. Each script has access to like its own set of registers and memory. This is a design decision that I made just kind of arbitrarily. There's not a specific reason for it, but we'll talk more about that when we get there. But the registers, there are 24 64-bit signed int registers, 14, or not 24, 26, 14 64-bit double registers, and then 12 vector registers, which is kind of strange. You wouldn't really see something like this in an assembly language, not the same way we're going to be implementing it. And each vector is a pair of 32-bit floats, single precision floating point. And what you'll notice here is that all three of these data types fit into 64 bits. Each script also has access to its own 8 kilobyte stack and 4 kilobytes of RAM, essentially. So here's just like a list of all the different registers. We have sort of the general purpose, like registers for each data type, int, float, and vector, they don't really have any conventions tied to them. Then we have argument registers, which I talked about last time, and return registers, same thing. Then there are these additional registers, which I've only included int ones. You could very easily include float and vectors if you wanted. And these are just like things to use by convention that basically just say, hey, if I'm a function and I'm going to use these registers, I need to save whatever's in them on the stack first. But for these other ones up here, which are usually referred to as like temporary, that's why it starts with T, that's not sort of the convention. And then there are 4 special registers, which I'll talk about here. So flags is kind of important. It's a bit more advanced. And I should clarify, special registers meaning that stuff that the like runtime environment of these scripts controls. All of these things will be left alone by the like virtual machine, I guess, that's running these. They are like whatever value you put in there, it'll stay in there. But these 4 down here are all set to some degree by the environment itself. So flags is set to 0 at the start of each script execution. And then within your script, you can sort of write to this register and set certain bits to signify certain things. And then whatever object is running this script will receive this value. That's like the return value of that script being run. And so like you can set flags in there to say, hey, this thing happened, and then the object running that script can see and set whatever state it needs. So the example I gave here is like some item class that needs to store, like in C++, the C++ object needs to store the time at which it was last used. And so you can set a bit in the flags register to say, like, if I used this item, this frame, set this bit to 1. And then the item object will receive that flags thing, and it can see, hey, is this bit set? If it is, I'll just store the current time as like the last time I was used, that kind of thing. But we won't be doing too much with that. That's more for like you to extend on this functionality yourself if you want. The biggest 3 are these object, host, and object count. So object is like a special register in the sense that it's not quite like the other 3. Like its value is not set by the runtime environment, but it is used implicitly by all of the instructions that operate on objects. Like whatever value is in here is the value that will be used by those instructions. And essentially, this is just an index into an array of scriptable objects. And whichever index is in here, that scriptable object will be operated on, that kind of thing. Host is just like a special. It's almost a useless register, but it's basically just to make your code more readable. It's a special register that, for our case, will contain the value -1 every time. Like that value will be reset every time the script is run. And this is the value that signifies, when you move it into the object register, that, hey, I'm not operating on just any like scriptable object in the array. I'm operating on the host object, the scriptable object that is running this script. I want to operate on that one. And then object count just has the number of scriptable objects that are part of the array of scriptable objects, and that's, I'll refer to that as the environment. So when a script is run, it'll receive both the scriptable object that is calling that, the host, and then also an array or vector of other scriptables called the environment. And object count here will store just the length of that, the number of objects in the environment. And the way it's that we're going to implement it, again, this is sort of a thing like determining what the environment is and how you collect objects into the environment and so on, is very implementation dependent. So we're not really going to be doing anything with that. We're just going to be setting it up so that it's possible. So like by default, dynamics don't consider anything as part of their environment, so object count will be 0. But camera, we are sort of going to use it a bit. Camera considers its target as part of the environment. So object count will be set to -1 or just to 1, and the only object in that environment will be the camera's target. Okay, so talking a bit more about memory, we have the stack, which I talked about last time. It's basically just for situations where you need to call functions. It's 10,024 64-bit words, so 8 kilobytes. The type is not important. All stack operations, there's no casting done. It's just the bits are copied directly. And the only like direct interaction that you can have as a programmer with the stack is via the push and pop instructions, and those handle the stack pointer automatically. The call and return instructions, which are used for calling functions and returning from functions, which I talked about last time again, those also make use of the stack, but all of that is sort of hidden from the programmer, just because there's only one correct way to do it, and so there's no reason for us to make the programmer do it. We can just abstract that away. But they are typeless, so you can do interesting things like load some value into an int register, push that int register onto the stack, and then pop those bits off into a floating point register, and then print the result. And it's not really useful, but I always think that's cool. So each script, in addition to the stack, also has access to 4 kilobytes of just general purpose RAM. And the instructions for operating on this are the load memory and store memory instructions, which operate on 8 bytes at a time. And string constants used within your code are actually just automatically stored into this memory. So I'll go to Paint for this. If we have, like, I'm not going to draw all of this out, but we have like 4096 bytes of RAM, of memory. So let's say we start at like 0, and then we have ... with this being index 4095. And then say we have some like instruction in our code that uses a string constant. So this might be just like printing a debug string, just for while you're like writing a script and debugging stuff, or it could be like setting an object state to something. So like if you're moving, you would set the state to move. These string constants will automatically be stored in RAM for you. And like when these scripts are, I guess, compiled or assembled, those will be replaced with like a pointer into this memory, essentially. So for this one, for like move, we would have, this would be stored in memory as MOVE and then the 0, like the /0, null terminated string. And then if we had like another string that we were going to use, just something short, because I want to fit it in here. let's say ABC, ABC would just be stored at sort of the next, like the next available slot. So it starts at the bottom of memory at the lowest index and then works its way up. And that's just sort of for convenience because it's easier to think about as the programmer, like starting to use memory from 0 rather than starting from the bottom or anything. If these were automatically put at the top of memory. So I just decided to put these at the bottom. Okay, now we have the list of instructions. We're not really going to look at this yet. We'll do so more when we actually start implementing them. But I'll just sort of scroll through them. So we have like all the basic math stuff. We have some bitwise stuff, some trig and other functions, some vector functions, memory stuff, stack, memory, moving stuff around in registers, control stuff, so jumping, calling, branching, sleeping, blocking execution, just some convenience debug functions for printing stuff, and then all the engine functions, so manipulating objects and getting input, but we'll look at all those more in detail. Labels, I don't think I want to go into now either, and then we just have some examples. So yeah, I think I'll leave it there and we'll actually start writing some of this now. But again, I'll have this linked below if you want to read over it yourself, which I kind of recommend because this is super complicated and it'll just be nice to have a reference like that, hopefully. Okay, so I'm going to start by creating a brand new folder in our source folder here called script. So the first thing we'll do is sort of like outline our actual script like class itself, like the environment and everything necessary for a script to run. But then we will, I think probably for the rest of this session, we'll be writing the code for parsing a script, like actually reading it in from a file and how that's translated into an actual script object. And the next time we'll pick up with like going through that list of instructions and actually implementing them. First thing we'll do is a registers class. So this is just like an object to combine all of our registers into one thing, just for convenience. And we have quite a few constants here. So the number of integer registers we have, which is 26. Float is 14. And vec is 12. And we have these masks, which I'll talk about next time when we use them. But they're just like, because all of our registers are 64 bits, but these are like the upper and lower 32 bits. Then we have the special register indexes or indices. So the object, then the host, OC, and flags. Finally, we have the actual registers themselves. So we have 26 64-bit signed integers, 14 64-bit double precision floating point, and 12 vectors, which are just pairs of 32-bit single precision floating point. And before we get too far into this, we'll just come into vec2 and just make some convenience changes for ourselves. Just add a default constructor. And a constructor that just takes one argument. and sets both elements to that argument. Okay, that's it for registers. The next we have is command. So we sort of have two things in here. We have, well, three really. So in order for, and I guess I'll go to the spec for this. In order for like our parser to be able to identify mistakes in the code as it reads it, we need to make it so that each instruction can only take certain arguments, like certain argument types, basically. And these types are listed here. So we have I for int register, F for float register, da 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 da, and then combinations of those just sort of chained together with underscores for multiple things. So like for this one, I could say, okay, add v. The first argument must be v, so it's a vector register. Then I have a float register or a vector register or a float immediate. And then the third argument is also a vector register. So that's going to be called the arg type. And we'll just define all of those in an enum. We don't need anything fancy. So I'll have none for 0, just for like error cases. But then we'll have, so integer, float, and vector registers, integer immediates, float immediates. Then we'll have some other weird ones, which are basically just integers as well, but I'll talk about those when we get there. L for label, and string immediates, so string literals. And notice that these are all powers of 2. So this is like the first bit on the right, second bit from the right, third bit from the right, da 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 da. And because of this, we can OR these all together. And that's how we'll create like the combination ones. So IF, so an integer register or a float register will be I or F. So the value there is 3, but that doesn't even matter. Like all that matters is that these 2 bits are set so that it is identified as both this type and this type. And now I just have a bunch of like boring copying to do. And we could do these like as we use them, but I thought that would sort of make that part too choppy. Like it's not going to be super fun when we're actually finally implementing all these instructions to have to come back here and constantly add new stuff. It'll just, I don't know, break it up. It'll be annoying. Okay, then we'll just have a couple of convenience methods here. I'll just override the AND operator for arg types, because even though this is just an enum and these are just like integer values, the AND operator, like the compiler won't let you just AND on this type. Like you have to first cast to a uint, which is annoying every time I want to do that. So I'll just override that operator so we don't have to. And again, this stuff like won't make much sense now, but I'll come back to it and like explain it, I guess, when we actually use it. Okay, next we have command description. Which has well, a static value. Put in the opcode of the command and a list of arg types that are the args. So like for this add v, the opcode would be 0, 1, 2, and then the arg types would be v, this, and then that. So 3 different entries in that vector. Then we have args. And this like is just a structure that'll be passed to an instruction essentially, and it has all the information, like all of the stuff in the argument list that that instruction needs to use. So we'll have pointers to all of our registers. Well, not all of our registers, that's a bad way to say that, but a pointer to the registers that this instruction, like the invocation of this instruction will need. Pointer so that we can modify the value directly very easily. We'll also store the opcode, and then 2 integer immediate values, and 1 float immediate value. And this is something that I will definitely come back and touch on because this is certainly weird. Okay, so that's like the groundwork. Now we can just sort of get a skeleton of the script class going, and then we'll actually get into reading script files. So I'll forward declare some stuff here. We'll have this structure just for convenience. Just group some parameters together. And we have our script. So the first thing I'll do is type def some of these things. Just to save ourselves some typing and also make it easy to change if you want later on. We'll make the friend or the script parser class a friend of this one for convenience. I'll delete these as always. Okay, and then for now we'll just have one method, run, which takes in a script runtime, the host, the object calling this script, and then a vector of other scripts, which is the environment. Okay. That's all we have for public right now. I don't think we'll define those today, though. So we have the stack and like RAM that we need to give sizes to, and you know I don't like having magic numbers everywhere, so I just made these like constants. Now the stack, I've sort of written it a weird way just to make clear that like it should be 8 kilobytes no matter which data type you're using. But because our like word size effectively that I chose is 64 bits, each element on the stack is a ulong, which is 64 bits. So this just makes it so that it gives you the number of ulongs you need to get to 8 kilobytes. And then mem count, memory is just going to be bytes, so we can just give that straight up, 4096, 4 kilobytes. And then op count is the number, like the total number of instructions that are supported. So like this list here cannot exceed 128. And that is chosen somewhat arbitrarily, but that's another thing I'll touch on. And we have the host index value, the value that will be loaded into the host register. And we have some information about our different types of registers. This will be the index of each of our special registers. So we have object, host, object count, and flags. Notice that all the register names start with parenthesis or $. That's just something I chose because I think it looks nice and it makes it easy to differentiate between like register values and other values. Then we have the list of offsets for our non-special register types. So this will be these guys. So we have T, F, V, A, R, S, and then the special ones. So T, S, A, R, V, F. There are 8 of each of those. Okay, and then we actually have the like state information. So some booleans there. Our RAM, our program counter, entry point, and stack pointer. Remember I said last time that like program counter and stack pointer are traditionally, they're actually registers themselves, but in our case there's no need for that, so we'll just store them separately. We have our stack, and I've chosen to make this ulong. I described it here as the type doesn't matter because all operations are typeless. The bits are just copied directly, and so this could be any like 64-bit value, but I chose ulong because traditionally it seems like when you just have like a buffer of memory, unsigned integer types are used, and so I think that also just helps make it clear that it's like not any one of these types, so it's none of these in particular, it's just 64 bits for any type. Then we have our registers themselves, our actual list of instructions, and something we won't get to till way later, which is the spawn queue. Okay, then we've got some private methods. We have get x register, and these just take in an index. So like index will be like each of our register like names, like $T0 will be converted to an index. And then giving that index into this function, we'll get an actual pointer to that register. And that'll be part of the parsing process, so we'll see that today. There are 2 methods we will be writing as part of this class today. I can do those right now, which is stack push and stack pop. Okay, so stack push. First thing we have to do is that our stack is not full yet. So if our stack pointer is greater than or equal to our stack count, stack pointer just being basically an index into this array of ulongs. Then we have Stack Overflow. So we'll return. Otherwise, we will set the stack at like the current index equal to just the bits of whatever we've been passed. That's what pun does. Remember, just no casting, just get the bits directly. And then automatically increment the stack pointer there so it points to the next slot. And then stack pop will be very similar. We just check if the stack pointer is already 0, then we have stack underflow. And we'll just return 0 in that case. Otherwise, we will return the element in the stack at the previous index. So stack pointer is like the index in the stack at which to insert next, and so to get the previously inserted item, we have to pre-decrement that. Okay, so that's that. I think that's all we're going to be doing for this, like all we're going to be defining for the script class today. But we can do a little bit more groundwork, I guess. Yeah, I guess I'll do this now. I'll just go ahead and define a macro. Because all of our like instructions, they're just going to be functions. And they have the same function header, and so we don't want to have to copy that every time. It's just a pain. So we can write a macro to just replace that text for us. And then we want to just define that macro for like this portion of the compilation process, because I is like a terrible name. We don't, and this doesn't need to be accessible anywhere outside of this code anyways. So that's just for convenience, but then we have some stuff we actually do need, like storing all of these operations and data about them. So I'll just do a type def here on this function, or this function header. And that'll be called operation. Remember, this weird thing here just means it's a pointer to a member function of the script class, and I'm calling it operation. So we'll have an array of function pointers. Then we'll have a map that maps the like opcode, the index, to the name of the command. And then a map, I keep misspelling that, a map from name, the name of a command, to that command's description. And then all of these maps, like we could define them separately, or both these two maps in this array, we could define them separately, but like there's a lot of shared data between them, and so for every new instruction we define, we'd have to like copy and paste the same data everywhere. So what we'll do instead is just have a vector that we populate, or like manually populate, and that'll have this just like temporary instruction type that has all the information that all of these collectively will need. And then in our constructor, if these maps aren't if they aren't already populated, because these are static, they're shared across all instances of this class. So if these aren't populated already, then we will just sort of have the computer populate them for us, so we don't have to copy and paste a bunch of stuff. Which means that the only thing we'll have to do manually is write all that stuff one time in here. So like for the going back to this example, for like the add v instruction, I would give the name, so add v, and then I would need a vector of arg type, so that takes a v and an f vmf and then a v, and then I would give like the instruction or the function pointer, which we don't have yet obviously, but it would be like that. And then for each new instruction we add, we just have to add another line like this. But that'll come next time. Okay, now we have the script parser, and this is like the code that we're actually going to write this time. I think we'll be able to finish with it, hopefully. So this is sort of, it exists just to separate out the tasks of like running a script and handling all the memory stuff of a script, you know, the registers, the stack, all that, from the task of reading it in from a file and turning it into a set of instructions. I just decided to make that a separate file or a separate class. So we have our constructor here, which takes in the file path of the path to read, and then a pointer to the script to actually like populate based on what's in that file. Then we'll just have one public method called parse, which will actually read the file. And we'll have a bunch of private methods. So I'll have some like character constants here. Just that like signify certain things in the file. Like that, so I'll explain those as we get to them. And we have the line, so the current line, like the line number that we're currently parsing. And then the index into our script's RAM at which a string was last written. Because remember, this parser will take care of like looking at string literals in the code and then auto-populating the memory of the script. So this will store like the last index in memory that was modified. We'll have an unordered map of label names to the line that they point to. And then an unordered map of line numbers to labels that those lines reference, because labels can also be parameters or like arguments to an instruction for like jump and branch, stuff like that. We'll keep the file path handy just for printing errors. Obviously we need the input file itself. And then our script. Okay, now we have a couple private methods. We'll have parse line, which just takes in a whole line at once and figures out what to do with it. That'll be defined in a separate file. We'll have create, which takes like a split apart line, a line split into the command and its arguments. command or instruction and its arguments. I'll sort of use those two interchangeably, command and instruction. Then get arg type, which will be used on like the list of args here. It'll go through and parse each one of those and figure out if they are the right types. So like if I pass a float register as the first argument to the add v instruction, it'll say, hey, float is not one of the valid ones here, so I'll throw an error. Then we'll have a weird method called resolve int, which will take a string and turn it into an integer value. Then just for convenience, we'll have like a method to print an error, just because we will want like a common error format across all of our errors, so might as well abstract that as much as possible. So we have s printf. Yeah, I'll just write this then explain. So in like trying to abstract this out into a method, we sort of lose the ability to provide any sort of formatting. Like if I want an error that prints out like the name of the string of the argument, the incorrect argument that was provided, I can't account for that in like the generic error function. So instead what we do is we have some buffer, and then we print, we take in a format string that's unique to each call of this, and then like add it on to this basic template, which just prints the file path and then the line number that the error is happening on. So it takes those, and then the format string combines them into one string, and then calls printf on that one string, which is kind of cool. So unfortunately in C++ there aren't like a lot of the common string utility functions that there are in other languages, like trim or split. So trim like removes any white space from the beginning and end of a string, but we can just write that ourselves. It's not that big of a deal. So we just find the index of the first non-white space character and the last non-white space character. And then if either of those are not found within the string, which means either like the string is empty or contains only white space, then we'll just return the empty string. Otherwise, we'll return the substring from start to end minus start plus 1. This is looks a bit weird, and I constantly mess this up because I'm used to the way like every other language does it, Java, JavaScript, where the substring method takes like the start index and then the end index, but this takes the start index and the length of the substring you want. So the length, we have to calculate that ourselves. Okay, next we have a bit of a more complicated one that's just like a super hacky implementation that is not super general case at all, but works fine for us, which is to take a string and split it by some character. In our case, we'll do that for the args list, because all the arguments will be separated by commas, and we want to get those, like each argument as a separate string. So we'll split by comma and return a vector of all the separated strings. And also, because we're writing this ourselves, we sort of have the added benefit of like we can add our own like weird quirk into there, which you might have to write something like this yourself, even if there were like a standard like string.split method, because our arguments can, or some of our arguments can be string literals, and those string literals like enclosed in double quotes, and those string literals can contain commas, but we don't want to split on those because, you know, say we have the arguments like, I don't know, 0, 1, and then hello, comma, world. Just like a default split would say, okay, 1, 2, 3. So I have 4 strings, when really that should be this. And so we can just account for that ourselves here. Where if the current character, we'll just go through the string character by character. And if the current character is the string token, which I've defined as the double quote, then we will flip the state of this string boolean. Otherwise, so if we're not in a string and the current character is equal to the delimiter character that we've given, we need to split the string here and like add a new substring into this string vector. And we will go ahead and trim the substring as well, because you could have things like we have like one argument and then a comma and then a tab and then another argument, and you don't want like this whole thing to be the argument. You only want the number itself. So we'll just trim that. And then once we're out of this loop, we'll just like put whatever's left and return result. So this is necessary because like, take this example where I hit this comma and I say, okay, add that to the list. I hit this comma, I say, okay, add that to the list. But this part, there's no like last comma here. So I'll just exit the loop without actually adding anything. So once I exit the loop, I just need to add whatever's left to my array. Okay, then we'll have next line, which takes in a string. And puts the next line of the file in it if there is one, and returns true. If there is no next line, then we return false. EOF means end of file. And this just gets the like index of a space within a string. I'm not exactly sure what that'll be used for. Probably just like chopping some stuff off. Yeah, I think just like chopping the white space off a line or something. Okay, so that's all we need there. But we still have these 4 big methods, and each of them are quite sizable, as well as parse up here. So let's get to writing those. And let me see how I'm doing on time. Okay, I'm about an hour in. I don't think we'll be able to finish all of this today, but we'll get through most of it. Okay, so we have, well, let me do all the includes first. Okay, we have this constructor, this method, and these. Okay, so the constructor, we're just gonna like set a bunch of our values here. Initialize our last string right, as I was saying, to the like bottom of memory, the last possible index. We start on the 0th line. And then we'll just check to see if our file is actually open. So if it's not, we can print an error. Yeah, we don't need to return. Okay, and then the parse method. So this is like the one public method. This will be like what drives the actual reading from the file and turning it into a script. So we'll have a string for the current line. And then while we haven't hit an error and there is a next line, we will increment the line index. If the current line is empty, we'll just continue because there's nothing on there to parse. Otherwise, we will parse line on our line. Okay, so that's just like going through each line of the file and reading it as much as possible. But there are going to be certain cases where like you can't just do everything on like a single read through. I should zoom in so I have more space. So like if I have like my main function that say calls another function called fib, and that function is defined somewhere down the line, then just going through and parsing this line by line, this will be like an unresolved reference and our parser won't know what to do with it. So we sort of have to like save that for later. And then once we've read the whole file, we can go back and replace that with whatever value it needs to be. So that's what we'll do here. So for each reference, which is like a use of a label as an argument, we'll first see if that label even exists. And if it doesn't, we'll print an error. And this is why we take in the line number as a parameter to this error function. We could just like use imLine here, but in this case that doesn't really make sense because, like, again, this is not happening sequentially. Imline is like we've already read through the whole file, but we will store the line number of each reference, and so we can use that in our like error to print the error. And then abort. Otherwise, so if this is like a valid label name, then we will use that line number. So we'll go into the instruction at this line number. And set the first immediate, because remember, instructions are just args objects, which are all of this stuff. And labels are considered immediate values because they're essentially just like, they're just numbers. It's just like a line number of another instruction, you know. And so that's why it's an immediate. It's just like an integer constant value. So we set that integer constant field of the instruction at the line that reference occurred on to the line at which this label is actually defined. Okay, then we can do one last check. To see if we have an entry point token, which is the string main. So a label called main, if we have that, then we will set our script's entry point, the index of the instruction to start on, equal to the line number at which that label is defined. But, you know, obviously this is an if statement, so that's optional. If we don't have a main label, then it'll just start from instruction 0, so just from the top of the file. And we can return not mabort. So if there was no error, we'll return true. Okay, so that's just sort of like the driver thing, but all of this is fine. But we need to actually the parse line function now, which is where everything else is going to happen, like turning stuff into instructions, populating this references list and labels or references and labels maps. So parse line is like really the big function here. Okay. So this, I'm actually not sure why I didn't use the trim function here, because all this is doing is getting the index of the first space in the string, and then the first non-space in the string. And if the space comes before the letter, it just yeah, I don't know. The trim function should work there. I'm not sure why I did that, but it might be for some reason. So I'll just leave that for you to change if you want. But I'm pretty sure trim would do the same thing. Okay, then we separate the line out into the command or instruction and the arguments. So the command will always be first, and that'll be just like the first part of the string until the first space. And the arguments will be whatever's left. And then we can trim both of those as well. So if the first character in our command is the comment token, or the hashtag there, then we'll just return, because this line is commented out, so it should be ignored. But if the back, so the last character of our command, is the label token, then we are defining a label on this line. Now I have the rules for labels outlined here. So each label must be on its own line of the file. So like this is not valid, this is valid. Multiple labels can point to the same instruction, but they also have to be on the same line, or their own lines. Label names can't be the same. You can't have two things called the same thing, two labels called the same thing. And labels have to have at least one instruction after them. So here, this is just like a graphical table to show you what that means. But these are just sort of like basically just arbitrary like requirements. Like I think it looks nice to format your code like this, and so because I'm writing this language, you have to write your code like that. You can't make these ugly decisions. I won't let you. And I don't know, that's kind of nice. So we'll actually be enforcing those here in our this if statement here. So if this line does contain a label, then we can enforce all those things. So first of all, if this line is a label, so the command, like the first word of this line, the first thing before the first space is a label, and we have some other stuff on that line, some non-white space, that's an error, because that violates this first requirement here, which is that labels must be on their own line. So we'll print an error. Otherwise, we can get the actual label, which is just the command minus the label token at the back, so just minus the last character. Once we have that, we need to make sure that it is unique. So if we already have a label with the same name, that's an error. But if all that's fine, we will just push this label back into our labels array, which is a map from string, so the label name to the line that that label points to or is on, and then return. So otherwise, if our line is not a comment and it's not a label, then it's just a normal instruction. So we will add a new instruction created from the command and the arguments to our script's instruction list. Which leads us to our next big function, create. So this is just going to generate like an object that can be added to our script's list of instructions. First thing to do is get the command description of this command, the command name that we've been given. And obviously if it doesn't exist, then we have an error. Oh, and this can't also be called args. Arg list. This is called args. We'll set the opcode. We can just get that from the command description. Then we need to check that all of the arguments are valid. So expected is the vector of like allowed argument types. And here's where we will split our string here, which is just like the rest of a line, so all of the arguments. We will split that into the individual arguments. And then this might contain arguments that are just white space. So we'll go ahead and remove any strings in this list that are just white space. And we can do that with this sort of weird syntax. So standard remove if takes a range, so 2 iterators. So we want the range to be our whole list and then a lambda. And it goes and operates, it puts every object in that list through this lambda, and if the lambda returns true, it removes, in quotes, that object. So in this case, we say remove if my size is 0 once I'm trimmed. So if I'm only white space, then remove. But it doesn't actually remove things from that range. It just returns an iterator to what the end of this list would be if those objects had been removed, but it doesn't actually remove them. And then we have to actually remove them ourselves with list.erase, which takes the result of this, so like the end of the modified list to the end of our current list. Kind of weird. And then the first check we can do is if we've even been given the right number of arguments. So if our current instruction only takes 2, but we've been given 3 or 1, we can go ahead and print an error. Otherwise, we'll actually go through all of the arguments and make sure that the types are valid. And this will use the getArgType method to actually take the, because this list is still just strings, right? So we don't know what those values actually are. If it's an immediate value, if it's a string, a label, or a register. That method, which we'll write in just a minute, will tell us what the type of that argument is. And if the current, like the argument types that are expected at this index, ANDed with the current argument type is 0, then we have an error. And this is why all of our arg types are powers of 2. They're just like that, like you can combine them together and there's no overlap. This is why that's important, because it means that if I have, something that takes an I_f, so an integer or a float register, then this arg type is only going to be one of those. It's only going to be an integer register or a float register, or it could be a vector register or one of these or any of these. So our getArgType function is only going to return one of these like base values, none of the combined ones. So to check if the argtype of a given string is like valid within this, we just AND it together, just do the bitwise AND. So that's all that loop does, just checks that they're all valid. And then now we go and actually generate an argument, like an argument object. We actually fill this structure out. Okay, so if our arg type is a label, we can't do anything with it yet, because eventually it needs to be replaced with an index, because that's all a label really is it just says, hey, jump to this instruction. But all of that is, it can't be done until the end, once we know what all the labels are called and where they point to. And so all that's handled by this. So in this function, we'll just skip over label arguments. Otherwise, we will turn the current argument into an integer, which is kind of weird. But I'll explain why that's necessary right here. So any argument can resolve to, it can be like one of these types. It can be a register, an integer immediate, a float immediate, a label, or a string immediate. So labels, obviously, we're ignoring because we just skip. String immediates are essentially integer immediates, so I'll also skip those. Registers are just strings. They start with a $sign and have some, like a letter and number after them, which are turned into an index. But then these two are where the trouble is, because these four types here are all integer values, but this is a floating point value. And I just wanted like a method that I could give a string and it would give me back a valid numeric value, whatever the type of that value is. If it's a float or an int, it doesn't matter. I just have one method for it. And there might be a better way to do this, I don't know, but I just decided to go with the pun, the macro that just copies the bits. So our resolve int here, instead of just returning an int, it returns a pair of an int and a bool. And if the bool is set to true, it means this is a float value, even though obviously it's returning an int. It's a float value. And I don't know, this is kind of weird. This is more of a remnant left over from when I was still like actually turning all of these into 64-bit word instructions. And so, you know, I'd have to fit floating point values, like those are just bits. I'd have to fit those bits somewhere in a 64-bit integer. And so I just got all of them, all those bits as an integer type anyways. I don't know, there's not a good way to explain it, but as I sort of talked about last time, I didn't end up doing that for this just because I didn't feel like there were enough valuable reasons to for our cases. Or, well, I don't know. I talked about it last video. I'm not going to repeat what I said. But yeah, there's probably a better way to do this with templates. But just know that that's what this is, and we'll write that in a second. So this is just the case where the current type is an immediate type, which, you know, we have this function here. So if an int immediate or a string immediate, which that's why I said string immediates are basically just int immediates. If it's one of those two or a float immediate, then we set these values, the immediate fields in this arg structure. Otherwise, it's going to be a register. The current argument is a register, some register. So if it's an int register, then this part, the integer field of the pair returned by resolve int, will be the index of the register that it is. And that index can be passed into these three functions to actually get a pointer to that register. We have the case of int register, float register, and vec register. Okay. And then we'll just return. So to sort of recap, because this is a very big method, we take in a command, so the instruction to perform, and then the arg list, which basically is just the rest of the line other than the command. We look for a command description. If it doesn't exist, then we have an invalid command. Otherwise, we continue on. So we just get the opcode here from the command description, which is part of this whole thing, like I sort of talked about, but you'll really have to see that next time. Otherwise, we were given a valid command, so we check its arguments to make sure all the types line up and the number of arguments lines up and everything. And then after all those checks pass, we just go through each argument individually and determine like which part of this arg structure it should be and set that to the appropriate type. So if it's an immediate, then we set one of these three fields. Otherwise, it's a register, so we set one of these fields. And then once we're done, we just return the args. Okay. So how are we doing on time? 125. Okay, I think I'll do this get arg type method because it's pretty simple. And then we'll pick up next time with resolve int and then actually doing some of the script stuff as well. So our get arg type, as I said, takes in some string and returns one of these values. So we have to determine which type of value a given string is. So if our string starts with the string token, which is the double quote, then we know it is a string immediate. That's easy. That's... Oh, why'd I call that arg list? Yeah, that's not right. That should be arg list. Okay, so if the first is a string token, a double quote, then it is a string immediate. And I should probably clarify this. I've said several times that string immediates are just integer immediates, which is true. They are, because of the way that strings are handled, they're just sort of automatically stored into memory. And so all a string immediate is like, to the programmer, it's a string literal. Like you type in double quote and then whatever string you want. But to this parser, it will put that string in wherever it belongs in memory. And then, which will be part of the resolve int function that we write next time. And then that location in memory will be returned in what is actually used for that instruction. That instruction takes in basically a pointer into RAM and then goes to RAM and reads whatever value that is until it hits the 0 character. It's a null terminated string. Okay, so that's if it's a string. Otherwise, it can be a label, in which case the first character is some value, some alpha value, some letter. Letter is the word I'm struggling for there. It's a letter. Then we just place a reference into our references list at the current line. Current line being instructions.size. The reason the current line here is not mline is because mline is incremented every time we read a line from that file, but the file can have empty lines, and there's not, like, we're not going to put like a no-op instruction into our script when there's an empty line. We're just not going to add anything. And so when I'm like doing error reporting here, I'll use mline because that's what the programmer sees. But when I'm doing a label reference, like the line that happens on is not the line in the text file. It's it's like the index of this instruction in the script's list of instructions, which won't always match up with the index of that instructor, like the line number in the file. And just to clarify once again, labels are like the name, the string to the instruction number that those labels point to. References are an instruction number that use a given label. And in this case, because get arg type is only used to resolve arguments, like we know that it's a reference because label definitions are handled way up here, where we check if the last token is a colon, then we create a label. But if it's an argument, then we know that we're using a label. And we have a special argument type for that, which is L. And labels actually are also just integer values, but the reason those aren't like an MI, basically, is because we don't want to be able to do, like, you shouldn't be able to pass a label to just anything that takes an integer value. Like, it wouldn't make sense to pass a label to the add function. That there's just no case where you should be able to do that. So this is purely like a parser only construct that labels are different than integers, when really they're just all numbers. Okay, so if it's not a string and it's not a label, it might be a special register, in which case we can go through this list of, or this map of special registers that we have here, and just return, well, see if this argument is a special register. And all of the special registers just happen to be integer, so we can just like hard code that return argtype I. Otherwise, if the first character is S reg token, we have a non-special register, and all register names should be of length 3, because we have, like, the prefixes are tsarv and f, so just one character. They all start with a $sign, so that's 2 characters, and then all of them have a single-digit number after them. You can see that here, all of the non-special. So the special ones we've already taken care of. These are the other ones. They all have $sign, some letter, and then a single-digit number. So it should be of length 3. Otherwise, we have an error, and I decided to just use a label in C++ itself, which you may not have known you could do, and I don't know if I've ever actually used one other than this, but this is just nice because it makes it easy to write this. So if our label argument is not a string of length 3, then it's some invalid label. So we will just report that and return like our error none argument type. Otherwise, we can get the 2 components. So we know the first character is a $sign, but the important ones are the second, which is the letter, and the third, which is the number. Now I'm just going to have a bunch of like range checks to determine the type of this register. So if it's a T or an S register, and it's a valid number, so from 0 to 7, then it's an int register. Other case where it's an int register is if it is an argument or return, and it is an index between 0 and 2. Next we have float, the float register. So if C is F and N is between 0 and 7, then it's a float. Or if C is A or R and it's between 3 and 5, then it's also a float. And lastly, we have vector. So if it's V and between 0 and 7, then it's a V. Or A or R, and it's between 6 and 7, then it's a vector. Okay, so we have string literal, label reference, special register, regular register. All we have left to do is immediate values, so like integer and float constants. Now, there is certainly a better way to do this, but I didn't put much time into thinking about it. So the only way I differentiate between float immediates and integer immediates is if they have a period in them. So float immediates must always have a dot. So like if you just wanted to write 1, but as a float, you would have to write 1.0 or just 1 dot. But if it's an integer immediate, then we know that the first value is either a numeric digit or the negative sign. So we can just say that it's an integer immediate. So this is like half the battle, basically, with our arguments. Like, this takes a string and tells us the type of it. The other half of this is taking a string and then actually converting it to some integer value. And we'll sort of have the same structure of like, okay, what if it's a string? What if it's a reference or a label? What if it's a special register, immediate, all that stuff. We'll do that in our resolvent function here next time. Let me just check time once again. Oh yeah, I'm already over 1:35. Okay. So yeah, I don't have anything left to say. Hopefully this was interesting. Hopefully, like, I've done an okay job of explaining it. I feel like in the script stuff, like, maybe I should have waited to write this until next time, or at least some of it, just because I just sort of wrote it and then left it there. But I do think it was valuable, and hopefully you agree, for you to see like how all of this stuff is actually going to be stored, where our instructions are just member functions of this script class, and then we store all the metadata about them in these various structures. But yeah, next time we'll finish off parsing our scripts and then get to the point we'll like implement all these boring basic things and then actually start writing scripts in our files and compiling them and running them, which is super exciting. So we'll do that next time. I'll see you then.